Hello, my name is Fraser Baird, and I'll be presenting our poster on searching for Forbush decreases in the measurement of neutron detectors for soil moisture. The co-authors for this work are Alex Hans, Keith Ryden, and Clive Dyer, all from the University of Surrey. About a decade ago, hydrologists started monitoring the ground level neutron flux above soil with the goal of measuring how much water is in the soil, or the volumetric water content of the soil. This technique is underpinned by the moderation of fast neutrons, which are generated in cosmic ray air showers by water. The technique is popular now, and there are over 100 detectors worldwide, and 51 in the UK network, which is called Cosmos UK. The Cosmos UK network has boron trifluoride proportional counters, which are surrounded by a polyethylene moderator. And because the network has such a high spatial resolution and large extent, it could be a valuable asset to the space weather community if it can monitor space weather driven variations in the primary cosmic ray flux. Our poster describes the systematic search for Forbush decreases in Cosmos UK data. Forbush decreases are decreases recorded in the count rate of cosmic ray detectors, and they're caused by disturbances in the heliosphere modulating primary cosmic rays as they pass Earth. We search for Forbush decreases by using an algorithm which looks for sudden decreases that occur across the Cosmos UK network. Our search period was from January 2015 to June 2021. This work follows on from a previous work which assessed the sensitivity of the Cosmos UK network to ground level enhancements in the neutron flux. Before we used the algorithm to perform the search for Forbush decreases, we took the data from each Cosmos UK detector and corrected it for variations in pressure and humidity, and we then performed a linear regression between these corrected data and collocated independent soil moisture data. We used the results of this regression analysis to apply a first order volumetric water content correction to each station's detector data. At this point, we sorted stations into bins by cutoff rigidity and averaged all available data in each bin. This gave us a single time series for each bin of the average corrected neutron counts in that bin. So we then fed these time series, which also had a 12-hour rolling mean applied, one by one through the algorithm to find decreases. The algorithm we used was first reported by Light et al., who used it to identify Forbush decreases in neutron monitors. We recorded every decrease, which lasted longer than 6 hours, and only kept those which were found in 3 of the 5 bins. For each concurrent decrease we identified, we also consulted data from 5 neutron monitors, interplanetary magnetic field data, and DST index data to check for signs that space weather, which might drive these decreases, was really occurring. Because the volumetric water content correction is only a first order estimate, we also reviewed all available volumetric water content and precipitation data to check if terrestrial weather might still be driving these decreases. The analysis identified 16 decreases in total. Of these 16, 9 are very likely driven by space weather. These include 2 decreases in September 2017 driven by CME impacts, which are shown here in figure 3, and another driven by a CME impact in July 2017, shown in figure 4. Of the remaining 7 decreases, 4 appear to be likely driven by terrestrial weather, and the cause of the final 3 remains unclear. They exhibit enhanced diurnal variations, and more work is required to ascertain the cause. To assess the efficacy of the VWC correction, we reran the analysis without applying it. This resulted in 53 decreases being found. Assuming 7 of the original 16 decreases are caused by terrestrial weather, we can see the correction removes 84% of the decreases driven by terrestrial weather. To sum up, We've successfully detected 9 Forbush decreases, which is a positive indicator that these neutron detectors can be used to detect space weather-driven variations in the ground level neutron flux. The empirical correction factor for volumetric water content variations is very effective, but not perfect. It may be breaking down due to rain or snow pooling above the soil, and thus the increase in hydrogen near the detector isn't accompanied by an increase in the measured volumetric water content of the soil. Some events remain unclear in their cause, and further investigations are required to find the drivers. Finally, our detection of Forbush decreases supports our earlier modelling work and suggests that these networks will be able to detect ground level enhancements of the atmospheric neutron flux. We have listed here our thanks to those colleagues who provided funding, support and data, as well as a reference list. Thank you for watching this poster presentation.